Welcome to this explainer. Today, we're unpacking one of the absolutely most fascinating technological marvels of the modern era. We're going to dig into the brilliant physics and the really intense engineering it takes to grab a massive, heavy, screaming loud fighter jet and transform it into nothing more than a tiny, almost imperceptible blip on a radar screen. It's literally a masterclass in applied science, so let's jump right in. Okay, so here's our roadmap. To really wrap our heads around this incredibly complex feat of engineering, we're going to break it down into a structured framework. First up, we'll bust a pretty persistent myth. Then we'll walk through the three pillars of stealth. That's geometric shaping, absorbing energy, and design integration. And finally, we'll talk about the actual limits of this technology and how adversaries are actively trying to beat it. All right, let's kick things off with Section 1, the Great Myth. Are stealth aircraft actually invisible to radar? Well, let's just shatter that sci-fi preconception right out of the gate. Stealth aircraft are not invisible, period. That's a concept we absolutely need to internalize. Stealth is actually an incredibly pragmatic engineering discipline, officially known as low observable, or LO, technology. Honestly, no aircraft in existence can fly through a radar field and leave zero trace. Instead, this tech is specifically designed to manipulate the electromagnetic spectrum. It reduces the range at which a jet can be detected, fundamentally delaying enemy targeting. Basically, it's all about buying the pilot a few precious seconds to shoot first. To put that into perspective, think about a conventional F-15 Eagle. It's an amazing, legendary fighter, but on a radar screen, it has a massive radar cross-section of 10 to 25 square meters. It's a huge target. Now compare that to the stealth F-22 Raptor. Its radar cross-section is just 0.0001 square meters. Guys, that is the size of a marble. Imagine a massive jet, fully loaded, appearing as a tiny little marble to enemy radar. It's just astonishing. And you know what's really wild? The history behind how we even got to that marble-sized signature. It's a massive historical irony, really. America's stealth dominance was actually born from an ignored 1962 Soviet physics equation. A Russian physicist named Pyotr Ufimtsev theorized that a radar signature depends on an object's geometric edges, not its overall physical size. Well, the Soviets completely ignored it because the shapes you'd need to make it work were aerodynamically terrible. But engineers over at Lockheed's Skunk Works division found it, translated it, and created a computer program called Echo-1 to calculate those faceted shapes. That led to the Have Blue demonstrator in 1977, which directly birthed the F-117 Nighthawk, the world's very first stealth attack aircraft. Which naturally brings us to Section 2, Pillar 1, geometric shaping. Shaping is the absolutely critical foundation of all of this. In fact, geometry alone is responsible for a staggering 90% of a platform's radar cross-section reduction. Materials matter, for sure, but shaping comes first. To get why, you have to understand the physics of specular reflection. Think of a radar beam hitting an airplane kind of like a flashlight hitting a mirror. If that mirror is perfectly flat and facing you, the light blinds you, right? But if you tilt the mirror, the light bounces off into the darkness. That's exactly what planform alignment does. It forces all the major structural edges, the wings, the tail, the inlet lips, to share identical sweep angles. This predictable alignment bounces incoming radar energy away into empty space, exactly where no enemy receiver is listening. But you also have to eliminate corner reflectors. A standard right angle, like where a vertical tail meets a horizontal wing, act basically like a bicycle reflector. It catches radar energy and bounces it perfectly right back to the source. So stealth designers meticulously eliminate these right angles. For instance, the F-22's twin tails are canted outward at exactly 28 degrees. Even the tiny little landing gear doors have these serrated, saw-toothed edges, so they don't form straight rectangular lines that might flash on a radar. Okay, moving right along to Section 3, Pillar 2. Absorbing energy. So, shaping handles 90% of the problem. But what about that remaining 10% of electromagnetic energy that geometry just couldn't deflect? Well, that remaining energy is handled by radar-absorbent materials, or RAM. These highly classified materials basically act like an electromagnetic sponge. Take iron ball paint, for example. It's quite literally filled with microscopic carbonyl iron spheres. When a radar wave hits it, the material induces a magnetic current that resists the wave, essentially converting that incoming radar energy into tiny, completely harmless amounts of thermal heat, which just safely dissipates into the airframe. Carbon composites and magnetic absorbers do the exact same thing across different radar frequencies. But, as you can imagine, this creates an immense logistical headache, often just called the maintenance problem. These RAM coatings are incredibly fragile. They degrade rapidly from moisture, extreme temperatures, UV radiation, and the brutal physical friction of supersonic flight. Because of this, bombers like the B-2 Spirit require highly specialized, climate-controlled hangars. Maintainers even use a specialized, classified material, literally nicknamed butter, to manually seal the tiny gaps between access panels, just to make sure radar waves don't get trapped inside the cracks. Which brings up a very practical question for you. How in the world do you hide a jet engine? I mean, you can shape the outside and you can paint the outside, but a jet engine is a giant, spinning metal fan designed to suck in massive amounts of air. And that leads us right into Section 4, our third and final pillar, design integration. This is where the whole puzzle has to come perfectly together. Protruding antennas, external weapons pylons, and especially those spinning engine compressor blades create massive radar returns. If you don't manage the internal hardware, all that brilliant external shaping we just talked about is completely useless. To hide the engines, engineers use what are called S-ducts. These are serpentine, curving intake tubes that bury the engines deep inside the fuselage. So, when a radar wave enters the intake, it just bounces around the curved walls of the S-duct, losing energy into the radar-absorbent coatings at every single bounce, completely blocking the radar's line of sight from ever hitting those spinning blades. It's the exact same reason all missiles and bombs are hidden inside internal weapon bays that only open for a split second to fire. And design integration goes way beyond just radar. It's a multispectral challenge. An F-22 flying at Mach 1.5 generates skin temperatures over 100 degrees Celsius just from the friction of the air. To an infrared sensor, it looks like a roaring bonfire in a dark room. To solve this, stealth jets use bypass air mixing and special V-trough exhaust decks to rapidly cool down the jet blast. To reduce acoustic noise, they use flat slot nozzles to slow the exhaust velocity. And to stop their own active radars from giving away their position, they use low probability of intercept radars, which randomly hop frequencies so fast that enemy warning receivers just think it's harmless background static. So, is stealth invincible? Let's get into Section 5, the limits of stealth. Because adversaries certainly aren't just sitting still. They're constantly playing a high-stakes cat-and-mouse game to break the magician's trick. The two biggest vulnerabilities right now are low-frequency radars and passive infrared systems. See, stealth is primarily optimized for high-frequency fire control radars, but low-frequency VH and UHF radars produce massive wavelengths, waves that are roughly the same physical size as the aircraft itself. Instead of reflecting off the sharp angles, these giant waves actually diffract around the whole jet, allowing the radar to detect it. Now, the catch here is that low-frequency radar is incredibly imprecise. It can tell you a stealth jet is generally in the zip code, but it cannot lock on tightly enough to guide a missile. That's where IRST, Infrared Search and Track, comes in, looking completely passively for the intense heat of the engines instead of using radar at all. But adversaries are getting even more creative with something called Passive Coherent Location, or PCL. Instead of emitting a radar beam that a stealth pilot's sensors can detect, a PCL system is entirely silent. It just sits there and monitors ambient signals of opportunity that already exist in the background environment, things like civilian FM radio broadcasts or 4G and 5G cellular networks. When a stealth jet flies through that invisible, chaotic web of everyday civilian signals, it causes tiny micropath distortions. The passive radar network analyzes those tiny fluctuations to covertly track the stealth aircraft's position without ever emitting a single pulse of its own. It's incredibly clever. So, where does this leave us? We're already looking at a future of engineered metamaterials that might actually bend light and radar around an object, or active cancellation systems that shoot out inverted radar waves to destructively cancel out the enemy's ping in midair. Which leaves us with a final thought for you to ponder. Could these next-generation technologies finally make radar detection permanently obsolete, or is stealth simply destined to be a never-ending, high-stakes technological arms race? Thanks for joining me on this explainer. I hope you found the engineering behind this as absolutely fascinating as I do.